In this video, we're going to look at how to construct a galvanic cell. A galvanic or voltaic cell is a spontaneous chemical reaction which generates an electric current. Since redox reactions involve electron transfer, galvanic cells use redox reactions to generate the electric current. Now, why are galvanic cells so important? Well, batteries are generally made up of galvanic cells, so of course they play a huge role in our daily life. So let's look at how to construct a galvanic cell using a zinc and copper. So first, let's say that we took a strip of zinc metal and placed it in a copper sulfate solution, like you can see here. The two substances would spontaneously react according to the following chemical equation. The solid zinc would react with the copper sulfate to produce zinc sulfate and copper solid. Now, this reaction only occurs in the forward direction. The reverse reaction does not occur. Furthermore, we can simplify this a little bit because sulfate is a spectator ion. So let's get rid of the sulfate and simplify our reaction, as you can see here. So the solid zinc atoms are going to react with the copper ions that are in solution to produce zinc ions, which go into solution, and solid copper. So let's look at this reaction at the atomic level. So here, this figure over here represents the zinc metal, and each of these would represent a zinc atom. So we have solid zinc over here, and over here we have the copper ions that are in solution. So we have our solid piece of zinc, and we have our copper atoms which are in solution. So what happens? Well, the copper ions are free to move around in solution, and when the copper ion bumps into one of the zinc atoms, you have an electron transfer. You have a spontaneous transfer, in this case, of 2 electrons. Now, when the zinc loses electrons, it's going to form zinc 2+, and the copper, when it gains 2 electrons, will form solid copper. So you can see that here. Now the copper, which is now solid, will precipitate or sink out of solution. And now that the zinc has lost 2 electrons, it's going to go into solution. So this zinc atom, which is now an ion, leaves the solid strip and goes into solution. Now this process continues. We get other copper ions bumping into zinc atoms. We have a transfer of 2 electrons, converting the zinc into zinc 2+ and the copper ion into solid copper. The copper will then precipitate out and the zinc ion will then move into solution. And this process will continue. And as it continues, the zinc metal will become corroded as the atoms begin to move away or get converted into zinc ions. We lose the zinc metal, it gets corroded, and the copper solution, of course the copper ions are getting converted into solid copper. So this process continues until either all of the zinc atoms are converted into zinc ions or all of the copper ions are converted into copper solid. So this is what it would look like at the larger scale. Here's what we start with. And you can see here, we've built up a lot of solid copper as it's precipitated out. You can't really see the corroded zinc, but underneath all that copper, the zinc metal would be much corroded. You also see that the blue color has faded a lot because of the copper ions are responsible for the blue color of solution. And as they form solid copper, we lose that bluish color. So that's great, but how can we use this reaction to generate an electric current? Well, to do that, we must construct a galvanic cell. How do we do that? Well, the first step to construct a galvanic cell is to divide our overall reaction into 2 half reactions. We want to take the 2 half reactions and separate them. So our half reactions, of course, here we have zinc going to zinc 2+. This would be the oxidation half reaction since we're losing electrons. And the reduction half reaction would look like this. The copper ions were gaining electrons and forming solid copper, so gaining electrons is reduction. So this is our reduction half reaction. So we want to take these two half reactions, and instead of letting them occur all in the same beaker, we want to separate them so that when the electrons transfer, the electrons have to go through some device like a wire or a light bulb or something. So let me show you how we would do that. Okay. So let's take two beakers to construct our galvanic cell. Let's take two beakers and let's call this one over here on the left. This will be where the oxidation half cell or the oxidation half reaction occurs. Over here on the right, we'll call this one the reduction half cell. So we're going to perform this reaction here, the reduction half reaction over here. Now it doesn't matter which one you put on left or right. I've just chosen them arbitrarily. So first thing, let's fill up this this beaker with some zinc solution. We need aqueous zinc. So I've chosen zinc sulfate. You could choose zinc nitrate, any soluble zinc solution. Now we also want to put a copper solution over here. We need aqueous copper. So again, I've chosen copper sulfate. So we fill copper sulfate over here, zinc sulfate over here. Now, next, we need some source of solid zinc. So I take a solid zinc strip of metal and submerge it into our solution that you can see here. Now we'll do the same thing over here. We need some source of solid copper for this half reaction. So we're going to take a bar of copper solid and put it over here. Now, what else do we need? Well, before we move on, let's look at a couple of definitions. The metal where the oxidation half reaction is occurring, we call this the anode. And the metal over here where the reduction half reaction is occurring, we call that the cathode. The anode is given a negative sign and the cathode is given a positive sign. So let's be sure to write these definitions down. The anode is the electrode where the oxidation occurs. It's where the electrons are produced and we give it a negative sign. The cathode is where reduction occurs. It's where the electrons are transferred to or consumed, and it has a positive sign. So be sure you're familiar with these terms. Now, we also need something, in order for our galvanic cell to work, we need something called a salt bridge. A salt bridge, this is a glass tube. So this is a glass tube with porous disc here. So it allows solutions to flow in and out of it. And we're going to fill this salt bridge with some non-reactive electrolyte solution. So something like sodium nitrate. This is very soluble. So we would fill this glass tube with the porous disc with a solution of, say, sodium nitrate. Well, what's the purpose of the salt bridge? Okay. Well, a salt bridge is a device that connects the oxidation and the reduction half cells, and it maintains electrical neutrality within our galvanic cell. Think about it. As the electrons flow, we're going to have a buildup of negative charge on one side and a buildup of positive charge on the other side. So the galvanic cell is going to maintain electrical neutrality. We'll show you how that works in just a second, but if there were no salt bridge, the solution in one half cell would accumulate a very large negative charge. The other side would accumulate a very large positive charge, and this would prevent the electrons from flowing towards the negative side. And the galvanic cell would very quickly stop working. The electrons would quit flowing. So we'll show you how this works in just a second. But let's finish our galvanic cell. We need to connect the electrode over here, our anode, to the cathode with some wire. So we've just connected them with some wire that will conduct the electricity. So what happens? Well, now that we've connected the two half cells, the zinc atoms over here in our solid, the zinc atoms are going to spontaneously begin to lose electrons. Those electrons are going to travel along the wire all the way over to our other half cell. The electrons are going to travel down the copper electrode and into the copper ions. So the zinc solid is losing the electrons, and when it loses the electrons, it's going to convert into zinc 2+, much as we showed you before. The electrons flow through the galvanic cell across the wire down into the solution where the copper ions gain those two electrons, and they form copper solid. So the copper ion is then converted into copper solid. So now we have a circuit. Okay, so we're having a flow of electricity, which of course is just the flow of electrons. So let's look at this just a little more carefully because this is very important. So over here on our anode side, the zinc, so here's my zinc atoms over here. The zinc will lose, each zinc atom will lose 2 electrons and they begin to flow across the wire. And as they lose the electrons, they are converted into zinc ion or aqueous zinc. The electrons flow down into the solution where the copper ions, copper 2 plus, will gain 2 electrons. You can see the electrons flowing down here into the copper ion. And as they gain 2 electrons, they are converted into solid copper over here at the cathode. So we have this half reaction occurring over at the anode, this half reaction occurring over at the cathode. Now, as the reaction occurs, the zinc anode will begin to corrode because we're losing the zinc atoms. They're going into solution. And the copper cathode, you'll see, will begin to build up a crust of solid copper around it. So this will occur over time. So this galvanic cell will continue to react until all of our zinc is corroded. Now, one other thing, again, back to the salt bridge. Remember, the electrons are flowing over from the zinc, from the anode to the cathode. So we're going to begin to build up a negative charge over on this side. So we're going to begin to get a very negative charge and a very positive charge over here as the electrons leave and go over here. So the electrons are not going to want to flow over here once we build up a negative charge. Negative charges repel each other. So this would very quickly stop working. Here is where we use the salt bridge. The salt bridge contains soluble sodium nitrate. Again, it could be any soluble electrolyte solution that's non-reactive. So the cations and the anions are going to maintain electrical neutrality. Remember, we're building up a positive charge over here as the electrons leave. So the anions, in this case nitrate, are going to begin to flow out of the salt bridge into this solution to maintain a net zero charge. So they're going to keep that. And over here, the sodium cations are going to flow over towards this negative charge. So the sodium cations will flow in here. So every time we gain electrons over here, the sodium cations flow over this way, and the nitrate will flow over this way to keep our electrical neutrality and keep the electrons flowing. So let's look back at our definitions here. We can add one other thing to it. The anode is what the anions from the salt bridge migrate towards. And the cathode is what the cations in the salt bridge migrate towards. So this is where the anode and cathodes actually come from. Anions flow towards the anode, and cations from the salt bridge flow towards the cathode. So be sure you're familiar with these terms. So here you can see our completed cell. The electrons are flowing, the ions are flowing from the salt bridge, and we have an electrical current. Now we can hook anything into this circuit if we'd like. We could hook a light bulb into it, so we could run a light bulb, we could run a computer, again, depending if it was powerful enough. So here, we could also just put in the middle here, hook it up to a voltmeter. A voltmeter measures the voltage difference between these two half cells. The voltmeter measures what we call the cell potential, which is a measure of the potential difference between the two half cells. So depending here, we're looking at zinc and copper, but we could make a galvanic cell out of lots of different substances, and each different galvanic cell would have a different cell potential. We measure cell potentials in volts, just like a battery. You've heard of 9-volt batteries, etc. The greater this cell potential, the greater the voltage, the more work can be done by that galvanic cell. So some galvanic cells produce a low voltage and they can't do a lot of work. Some galvanic cells produce a high voltage and we can use them to do much greater work. And we'll look at how to calculate cell potentials later, not in this video. Another note, the electrodes like zinc and copper. Here we have, in our galvanic cell, we used metallic zinc or solid zinc and solid copper as our electrodes. and they participated in the redox reaction. We call electrodes that participate in the redox reactions, we call those active electrodes. There's also electrodes that are inert, which do not participate in the oxidation-reduction reaction. They're just there in order to allow the current to flow into the solution. And we'll look at one of those in just a second. Often, these are used in galvanic cells where one or both of the half reactions do not involve a metal as either a reactant or a product. Inert electrodes are typically made out of platinum, graphite, or gold. So these allow the flow of electrons into the solution, but they don't actually participate in the reaction. So how could we construct a galvanic cell from this half reaction? If you would, pause the video and see if you could draw a galvanic cell from this reaction and label all the necessary parts, kind of like we did. Pause the video and give it a try before you look at the solution. So the first thing we want to do is let's break this into half cells. Okay? So we can see that the magnesium is going from Mg solid to Mg2 plus, so it's losing electrons. So this would be my oxidation half reaction. And then the reduction half reaction, I can see that the hydrogen plus is going to hydrogen 2 plus, so my oxidation number is going from +1 to 0. So here we have a reduction half reaction. So let's separate it into its two half reactions, and then let's convert it into a galvanic cell. So here's the complete galvanic cell. It doesn't matter which one you put on the left or right, but over here, here's the oxidation half. We have a piece of magnesium metal over here, and then we have some magnesium solution. I'm using magnesium chloride, but you could use magnesium nitrate, any magnesium solution. So we have our aqueous magnesium, and we have our solid magnesium. We have our salt bridge, which would contain something like sodium nitrate. And then over here, we have H plus and H2. Now, neither of these is a metal. So this would be an example where we would have to use some inert electrode like platinum to conduct the electrons down into the solution. So here we have our inert platinum wire, because again, this doesn't involve a solid that we could use as an electrode. So we have our platinum wire conducting the electrons down into solution, and we need some source of H plus. So we need some solution that contains H plus, which would be like an acid solution, like HCl, hydrochloric or nitric acid. And then we also need to bubble in hydrogen gas. So we need both of those substances over here in our reduction half reaction. Then we need to connect the two half cells by a wire. The electrons will spontaneously begin to flow from the magnesium over down into the solution, and they'll combine with the hydrogen to form hydrogen gas. And so this would be an example of a galvanic cell. And again, we could use that to do some work, just like a battery. So be sure that you can draw and label all of the parts of a galvanic cell, and be sure you understand the role for each part of the galvanic cell.